Sorry, I think the internet cut out for a moment. Objects are just these data structures that have fields on them, and we, have defined methods that operate on those fields. And hey, activation records are these data structures that have fields, so maybe we can, use this situation. And furthermore, when we the only problem is that in the traditional formulation of activation records, when you return from a function, right, we just remove the stack frame. We just go back up the stack, and that stack frame poofs into the void. And if you were in C or C++, this is exactly what would happen. But in JavaScript, right, we said, hey, these activation records can exist beyond when they are being used simply from a stack frame context. And this idea comes from Simula, right? So Algol was handling their activation records in the stack discipline. So when you entered a function, we'd allocate the activation record. When you exited the function, we'd deallocate the activation record. But Dahl was like, hey, we really like these activation records. They look like objects. We just need to free them from the stack discipline. So we need a GC to know when to actually eliminate them. But they were like, okay, we're going to decouple the activation records from the stack, and then we're going to use them as the basis for implementing objects. So how are we going to do this? So in Simula, the correspondence between normal object-oriented concepts and activation records is as follows. So what is a class? So traditionally, we think of the class as some sort of abstract definition saying what the behavior in an object was. So in Simula, they just said, okay, a class is just a function. Because what do functions do? Functions allocate they allocate new objects. They allocate a new activation record when they're called. So all we need to do is we need to just have one of these functions, create the activation record, because that's going to be our object, and then I just need to return a pointer to the activation record to actually get my hands on this object that was created. And so objects are just simply these activation records that are produced when I call the functions corresponding to a class. And then they need to add a little extra stuff, right? So normally you can't put your hand in an activation record and get out, fields in it. And Simula was like, okay, we'll just add a dot operator that lets us access variables inside the activation record. So a little bit of extra expressivity in this case. By the way, you might be wondering, why don't you have this functionality in modern language? And actually, in some schemes, they do have the ability to reach into activation records and get out their internal bindings. But most of the reason why people don't let you do it is because often they don't actually explicitly represent the activation record. It's some random stuff that is in C and has been optimized away. And so if they had to allow you at any point in time to give you that info, then it would be very hard to reconstruct what the fields were in that case. So a no-go for you. Okay, so we're going to look at some code in Simula, and to do that, I need to set up an example. So what is this example? So let's imagine that we've got a bunch of points, and we want to find the radius and the center of a circle passing through 3 distinct points. So algorithmically, how do we do this? Well, we just draw 3 circles around each of the points. The algorithm, by the way, is not that important, but I need to just set the stage for the code I'm going to show you. So we draw a circle around all the points, and then we look at the intersections for the circles, and we draw lines through the intersections. And the intersection of these 2 lines gives us the center of the circle that is passing through all the points. And then if you want to find out the radius, you just take the distance between that and one of the points that you were doing this from. So there you go. There's the circle. Okay, so we're going to model this in object-oriented style. So let's see what kinds of objects we need. So we're going to bring back the point object. So a point object has some sort of internal representation saying what its coordinates are. What operations does it support? Well, we'll support having comparing two points together to see if they're equal, and we'll also support computing the distance between 2 points, giving a real number. This is weird syntax. This is Simula syntax, but like hopefully it like kind of looks familiar, right? Like, you got your function arguments, and then after the colon is the return type. Then what's a line? Well, a line, if I have another line, I can test if they're parallel with each other. And I can also ask if I've got 2 lines, where do they meet? And this will return a point. And notice that this point returns a ref point. That's because we have to distinguish between pointers to things and the actual thing in question. So in Simula, you always have to write ref if it was one of these pointery object types things. And of course, if we have 2 circles, we can also ask where they intersect, and that defines a line, right? Because it's 2 points. Okay. So here is the source code, the actual Simula source code for a point. Let's just take a moment to soak it in. Obviously, you don't know the syntax, but there's some stuff that looks kind of familiar. You see a class, there's a begin and an end. There's some procedures. There's some white space that's showing us where the procedures start and end. Okay, let's step a little bit through it. So the first thing to notice is that inside this class, we give the types for the parameters after the function definition. This is just a Simula-ism. What's actually going on here is that we're defining the variables inside our block. So remember in JavaScript, the idea, right, is that when I call a function, I create an activation record and I put in all the parameters, and then I also put in all the local variable declarations. So people were not as good at implementing compilers back in the day. So they were like, why don't you just define a block and write down all of the variables, and so I can just know that I need a real X and a real Y to put in the activation record in question. So you end up with this weird thing where a class is like a function, and we also have to like say what the types of the arguments are, and they like exist on the same level as other intermediate allocations inside of the function. Okay. There's some stuff. Here's something that you might not be too familiar with. So if we want to test equality, well, we got a p as an argument, and if the p is not none, then I compute the distance between x and y, and if it's within some delta epsilon, then I equals that. What does that mean? Well, basically the way returning in Simula worked was there wasn't actually a return operator. You just assigned the return value to the name of the function. This is kind of weird, but like if you've ever written MATLAB or Fortran, actually that's how you return in those languages too. So it's a good trick to know. That's what it means in that situation. And there was a separate operator : dash if you were assigning a reference, which is what's going on with the point cases, right? Because when I allocate a new point, that returns an activation record. And so that's a pointer to some structure. Just to emphasize this again, when I define my function point, this defines a new lexical scope. So I can refer to the x and the y inside of the bodies of my functions. So I don't need to write self.x. I can just write x, right? And the reason why x points to something is because, well, this equals procedure is defined inside of the class point. So, the lexical scoping rules say, well, I can't find x inside equals, so I'm going to go look in my parent context, and in the parent context, I have x defined. So that's the one I'm going to get. By the way, this is like, this is basically the syntax, right, in C++ or Java, where you can elide this statement to refer to member variables. So it's really interesting to see it show up already here. Any questions about this code before I move on? Okay, so let's talk a little bit about how these objects were represented on the wire. So we have a pointer p that points to a point, and this points to an activation record. And this one doesn't actually have any access link. It's got its parameters 1.0 and 2.5, which are the X and the Y values. And then I've just written this in exactly the same way that I did the JavaScript representation, right? So now I have these procedures. The procedures are also just closures bound inside of this environment record where their access link points to the object in question. This is a little bit of a lie. This is a little bit of a ahistoricalism, because Simula didn't actually know how to do closures. They just had a special case for classes where they knew that if you call the procedure, the access pointer should go to the environment record for that class. But you can see how like our ideas from JavaScript map into this situation, even if Simula, you couldn't actually take the equals procedure and assign it to a variable. So here's some more sample code for line. I'm trying to so some more fun stuff. So once again, we define the class, and then we define the types of all the parameters, which are like local variables. And then we have a bunch of procedures just like before for defining parallel to and meets. And then you might notice that there's a bunch of extra code at the end that's not a procedure. What the heck's that? Well, remember that classes in Simula are just functions. And so you're not limited to just defining a bunch of methods. You can also do actual compute inside of a function. So you can think of this as, say, the constructor, right? It's the code that gets run when the line gets defined initially. And what's going on here is we're just basically we're just doing some stuff to check if the points on the line are too small. Okay. So here's another thing that Simula supported, which was inheritance. So you could define classes and then inherit from them. And the way that this worked was that we would take the activation records for each of the functions inside your subclass hierarchy and concatenate them together. So like in this example, D inherits from B, inherits from A. And we just say, okay, well, put them all together. And then, if I do a lookup on D, I'll first try to see if I've got the method or the variable there. And if I don't, I'm just going to follow the access link to the B part. And then if I don't find one there, I'm finally going to go to the A part. And so with access links, we get the behavior, which is that the subclasses get handled first, and then you go to the parent classes afterwards. There's one caveat that I want to point out based on implementing functions in this way. So here's some code, and I want us to take a look at it. Okay, so I'm defining a class A, and I define two functions on it, f and g. So f will return 0, and g will return whatever f is. In Simula, you don't need to put parentheses around function calls. You can just write the function, and that'll call it. And then we subclass b from a, and we also define a f on it, and we overwrite f to return 1 instead of 0. So the question here is if I allocate a b object and then I call the method g on b, what value do I get? And this might seem like an unfair question because I haven't really told you how to execute Simula code, but I want you to mentally compile this code into JavaScript, and I want you to tell me what JavaScript would have done in this situation. And yes, I'm going to wait. What is the value of g? Okay, there's one vote for 0. Anyone else voting for 0? So the reasoning behind this is that we have these activation records set up, right? And so when I call f, well, it's going to point to the ambient context that it was defined in, namely B. But if I call g, what is the ambient context that g was defined in? And so it turns out that in Simula, it works exactly the same way it works in JavaScript, which is, hey, you define G inside the context of A, so all of the variables G can reference point straight to A, and therefore, if I call F inside A, that will not go back to my class B. It'll just directly call the F that's in scope, namely the F on A. And Simula noticed this, and they were like, we don't want this to happen. So there's actually an extra virtual keyword that you can use to go back to the, most subclass object in this situation. By the way, I want to point out that the behavior in object-oriented programming, where when you call methods, it goes all the way back to the subclass object, it's useful, right? Because without it, you couldn't do things like hooks, where you define a bunch of interposition points in your basic algorithm that you can override later. But I just want to point out how strange it is to do this. It's not very natural to go all the way back to the bottommost class in the subclass hierarchy to go run your operations. And C++ agrees, right? C++ will force you to define a function as virtual if you actually want to do this. Okay, so to summarize, Simula was a hugely influential language. It defined what classes were, objects, inheritance, subtyping, virtual methods. It also even had some interesting features. So one feature is inner, and that's basically a way of combining parent code in the classes. And it also had inspect and qua, which in modern languages we would think of as instance of. Given a class, can I tell what instance it actually is, and can I convert a class somewhere else? And Simula also had some extra random language features for simulation, like it had a built-in concept for an event loop. And there's some stuff that Simula didn't do. So one thing Simula didn't do was encapsulation. It had no concept of encapsulation, and this got added later, actually, in later revision of the Simula language. They didn't have the idea of self and super, so we're going to see them show up in Smalltalk, right? Self being the idea of I want to refer to the current object, and super being the idea of I want to explicitly refer to the next activation record up, not the current one. They didn't really have class variables or exceptions, but these aren't really relevant to object-oriented programming, so I just put them in the slide because they're interesting. Okay, so to summarize Simula, so functions that return pointers to classes are simply functions that return pointers to their activation records. Objects are the activation records that are produced. You do subtyping by setting up a class hierarchy, and inheritance by pasting together these activation records. Seems pretty cool. And C++, basically will copy a lot of ideas from Simula when it's figuring out how to add objects to C. Any questions about Simula before we move on? If you remember nothing else, it's that, you can use activation records to implement objects. Okay, so Simula was a statically typed language, and I now want to shift to looking at more dynamically typed object-oriented languages in this history. And the first one we're going to talk about is Smalltalk, where the big idea of Smalltalk is everything is an object, even classes. Yeah, even classes. So what's Smalltalk? So Smalltalk, arguably Smalltalk is the language that made objects take off. Simula is arguably the first language that actually had objects, but getting it into the popular conscience for developers everywhere, that was Smalltalk. And the idea behind Smalltalk when it was being developed at Xerox was, hey, we want to come up with a language where there's one concept that rules over everything, and we're going to build everything out of it. And so in Lisp, in the languages we talked about, the big concept was functions, right? Everything is a function in the lambda calculus. But they weren't satisfied with this. And so they were like, hey, let's try to do this again, but with objects instead. And so if everything is an object, then all operations are done via messages to objects. There's a really lovely article about the history of Smalltalk from Brett Victor, and I highly recommend checking it out if you've got some free time for reading. Okay. And what was Smalltalk all about? Well, actually, Smalltalk was a language that was being built in service for this hardware concept called the Dynabook, which basically was a laptop. This is in the 70s, so this was a revolutionary idea in the 70s. But they wanted like a laptop that was a programmable, like it was basically be an IDE. So the operating system itself would be a programming language, and you would be directly interacting with concepts using a programming language, so that everything would be extensible in the same way that when you're in a programming language, you can write libraries and you can write new things on top of APIs. So pretty radical idea at the time. Dynabook, by the way, never actually worked out, and so if you ask some people, they'll say, hey, like Dynabook was cool, Alan Kay got a lot of credit for that, but like they never really delivered on it. But Smalltalk was a very influential language, and so there's a lot of interesting stuff we can learn from it. Okay, so the first thing I need to do is I need to explain Smalltalk terminology, and in particular, I need to explain what I mean by messages. Because I actually casually use this in place of methods, but unless you have used, say, Objective-C, this maybe is a bit of an unfamiliar terminology for you. So in Smalltalk, objects and classes mean the same thing that you'd expect in a modern context, right? Objects are instances of classes, and classes define how objects should behave. But then Smalltalk has these two interesting concepts called a selector and a message. So a selector is essentially a method name. It tells you what the name of the operation you want to do is, but it doesn't actually say what the argument values are. So you bundle up a selector with a bunch of values to form a message. And a message is essentially a packaged up method call, which you send to an object when you want to call the method on that object. So we're not going to use the terminology of calling functions or calling methods. No, we're going to think of Smalltalk objects as these little independent entities sending messages to each other to do various operations, right? And we're calling it sending messages, but really all it's doing is doing method calls. But it really lends itself to this like behavioral notion of objects, where an object is not just something where you can call code on it. It's actually a living, breathing entity that you send messages to. And it can choose to do things like, for example, forward on the message to another function. Or it can, for example, have a default message handler that handles cases when you don't understand what a message is. So the message analogy is pretty useful because it gets you thinking about other ways of interacting with objects that aren't that obvious when you're dealing with calls. And so then in Smalltalk, the method is just the code that knows how to respond to a message, right? So you get a message and you need to do something about it, and that's what the method says. And then you've got instance variables, which are the data stored in the object, and subclasses, which are incrementally modified versions of the parent class. So most of the terminology is very similar to what you know, except for selectors and messages. So how is Smalltalk going to work? So here are the ground rules. So 1, everything is an object, right? Even a class is an object, right? Objects have a class to describe what their behavior is, and the class is some entity in our system, and they're also objects, so you can also interact with them in the same way you can interact with regular objects. 2, objects communicate by sending and receiving messages. So there's none of this like directly reaching your hand into a object and setting some field, right? You're going to send a message, and that message is going to do something. And each object has its own state, right? Its own set of local variables that are associated with it that it can sort of modify or query when it gets messages. And then we'll set some other basic rules, which is that every object is an instance of a class. And to figure out what to do when you get a message, you look at the class to figure that out. And that's Smalltalk in a nutshell. Sound familiar? It should, right? Because this is how object-oriented languages like Python work. Questions so far? Okay, so let's look at some Smalltalk syntax. So, this looks kind of wonky, but let's just sort of chug through it. So, what do I got here? So, what I've got here is I've got a bunch of method definitions on a class. So, we're back to our good old-fashioned point class. So, what I've highlighted in blue are the selectors. And there's something very interesting, which is that Smalltalk supported something called mix-fix operators. A mix-fix operator is like an infix operator where you put the operator between the arguments. And what makes something mix-fix is actually you can have many, like sort of a single operator that is split up into many things. So like if I wanted x colon, y colon, z colon, I could do that. And it's logically one operator with 3 arguments to it. You can think of this as sort of like a proto version of keyword arguments because, it makes it a lot easier to tell which of the arguments is the x coordinate versus the y coordinate. So we've got a function called x colon, y colon. It takes an x coordinate and a y coordinate. And if you wanted to pass this message to the point, you basically say pt, that's the object, and then x colon 2, y colon 3. And that chunk, x colon 2, y colon 3, that entire thing, that's your message, right? The x colon, y colon is the selector, the 2 and the 3 are the arguments. And when you pass this message to the object simply by juxtaposition, that will cause the method in question to get run, which will set the internal state to x coord and y coord. Smalltalk is a imperative programming language, so there's a construct for mutable assignment. That's what the left arrow does. It just sets what the x and the y are, and to return from a method, you use the caret character. Don't ask me why. I guess they thought it was short. And these references to x and y, they're just referring to the instance variables inside of the object. So they're completely private and you can't actually access them directly. So for example, we have to write this weird thing, x, bar caret x. And that says, if you give me the x message, then I will return you the value of x. Because otherwise we won't expose the instance variable by default. Questions about this before we keep going? So let's look a little bit about how the representation for Smalltalk objects looks like. So we'll start on the left. So we've got a point object. The point object has a bunch of instance variables. X is 3, y is 2. And then the object is a class, right? Because we need some description of how to actually do operations on the object, and that's the class object. So this points to another object, which we're going to call point. And this object point contains a bunch of stuff, right? So one is it contains a pointer to the superclass called object in this particular case, which has behavior that I should defer to if I don't have an implementation for it in point. It also contains a template, which is necessary if I'm allocating a new point. I need to know what the fields that I should initially set up are, namely x and y. And it also comes with a method dictionary. And this method dictionary is basically a mapping from all of the selectors to the code that actually knows, the method code that actually knows how to run basically how to process if you're given a message with some particular selector. So, this is what the point class looks like, right? It's got a class name, point, superclass is object, It can define some class variables, some instance variables, and it also contains some class messages as well as some instance messages. One thing that I want to point out is that classes are objects too. So when we look at the point class itself, and we look at what's defined on it, we find that there are a bunch of methods on it as well. For example, here we have a method new xy, and what do we think that does? Well, what it does is it takes the object, it creates a new one. So let's step through this, right? Self space new. So self refers to the object in question, which is the class object, and new is a selector. It is saying, hey, call the new method on the class, the point class object. And point isn't actually going to define new. New is going to be a concept in the object class itself. But what it's going to do is it's going to give us a new point that isn't initialized to anything. And then what we're going to do is we're going to pass this object another selector, x colon y colon, which is going to set the x value and the y value. And then we're going to return it all, and that's the caret. So hey, you can read Smalltalk now. And if we want to define lots of different constructors for objects, that's as easy as adding new methods to the class in question, right? So we can also define new origin, and that just defines a new object that sets x to 0 and y to 0. And of course, when I initialize this class, I might want to define the class variable, and so I will just bind pi to be that. One thing that I just want to repeat is that you don't need like a concept of class methods or a concept of static functions or anything like that, right? If everything is an object, then things that work on instances go on the instance object, and things that work on the class without reference to an actual instance go on the class object. And you don't need to add any more concepts. It's all very simple. Okay, I just blazed through these slides, right? So saying the same thing, right? First send a new object to the self, new message to the self object, then send the mixed x message x colon y. Now, if you want to inherit, this diagram gets a little more complicated, but not too much more complicated. We have our class name, color point. We set up our superclass to point to point. We might have some new instance variables, say color. But remember, we also get all of the instance variables from our superclass point. We just don't have to reference them here. And then we might add some new methods or override some old methods to give some behavior for them. And so if we write this in diagrammatic form, it might look like something like this, right? A lot of arrows here, but it should make sense. We have our objects on the left. They point to their classes. The color point class points to the point class. And then we need to know what the template is and what the method dictionaries are. Okay, a little bit of fun trivia. So I said everything in Smalltalk is an object. So a class is an object. So what's the class of a class? Oh, getting a bit meta here. So in Smalltalk 76, their idea was, hey, well, we'll just say that there's a class object, and every class is a every point, the class of a point is class, and the class of a class is just class, because that's what class is. And this is the picture we'll have in the situation. And this actually works, but it's a bad idea. And why is it a bad idea? So the problem is, if we want to add a new class method, so remember, when I define a class, I put the behavior for how the instance should work on the class. So when I wanted to define like a method on point objects, I put it in the point class, right? That's where the method lives. So if I wanted to find a method on point, like one of these new XY methods, one of my constructor class methods, I have to put it on class. And so if there's a single class that is the class of all of my classes in my system, all of my methods get shoved onto this class object, and it's kind of a mess and terrible. So they didn't like that. So in Smalltalk 80, they're like, aha, here's what we will do. We will come up with a meta class. So what does a meta class do? Well, for every class you define, we will also define a meta class for it. So point is a class. And what is the class of a point? It's the point class. And now we can go ahead and stick all of our class methods on the point class for the description here. But of course, this raises a quite reasonable question, which is, what is the class of a meta class? So they were like, okay, well, okay, actually, I'm not even there yet. So we said points are a subclass of object, right? So I'm going to represent these relationships as the blue arrow. So a point is a subclass of object. Object needs to have a meta class, so that's the object class. And I want to inherit all of the methods that work on object class, like for example new, when I am implementing point class. So point class needs to be a subclass of object class. Okay, so now we have a problem, which is, what is the class of point class? And the answer is, well, let's bring back the meta class. So meta class is the class of the point class. And then the meta class, well, it needs a class. So it's going to have the meta class, which is the meta class of the meta class. And then the meta class's class will be a meta class. And actually, technically speaking, if you look at the Smalltalk 80 spec, object class and meta class are also subclasses of some other stuff, which I'm not going to put in the slide. Oh my God, what's going on? So, okay, so I'm not going to examine you on the Smalltalk meta class hierarchy, but I just wanted to point out that we can have good intentions, right? Our good intention was that we wanted to design an object system where everything was an object. And in the beginning, this seemed very reasonable, right? We just had we had a simplifying principle, and hopefully that made our system simpler. But when you actually work out all the implications, having a simple rule can lead to very complicated behavior. And sometimes it's a good idea. And in fact, like in modern object-oriented programming languages that allow a lot of dynamism, meta classes are a thing, and they are useful. And so like in Python, for example, you can define a meta class, and it is very mind-bending. And like, if you like read the Stack Overflow entry, which is like, when should I use a meta class? And the answer is, well, you probably shouldn't. But there are some situations where a meta class is exactly what the doctor ordered. And so, it is useful, even though it's a power tool, and most of the time you shouldn't use it. So yeah, meta class. Oh my God. There's a really good web page, which I didn't put on this slide, basically describing what's up with Smalltalk meta classes. And if you're really curious about what's going on there, I highly recommend checking that out. Okay, so to summarize Smalltalk, it's basically meta programming on crack. So you've got these classes, and they are telling you how objects should behave. And we had Smalltalk was encapsulated by default. So all the state was private. You only had public methods, but the only way to get at state was via these methods. Smalltalk's a dynamically typed language, so there's no explicit subtyping, and instead it's all implicitly done based on whether or not a object accepts a message or not. So Smalltalk is duck typed in this sense, because you can send a message to an object, and it doesn't have to inherit from it. It just needs to understand how to deal with that message. And then there is inheritance, and that's subclassing, and that's self, and that's super. And hey, that's pretty cool. Okay, I'm not going to get through, maybe I can get through this. Okay, so the last part of my lecture is self. So self looked at Smalltalk and they're like, I liked that idea. You know what? I can finish this off next week. Are there any questions about Smalltalk before we move on? I'm not going to rush. If I get cut off at the end, I'll just finish up next time. Okay, so the idea with self was Ungar looked at Smalltalk and he was like, wow, Smalltalk is cool. I really like the idea that everything is an object. But this classes, meta classes, ridiculous. Like this is just horribly complicated. So let's redo this idea. Everything is an object, but we are not going to have an idea of classes. And so if you don't have an idea for classes, what are you going to do instead? And so Self pioneered this idea of prototype-based object-oriented languages. And we'll explain very shortly what I mean by prototype-based, but we talked about JavaScript right at the very first lecture in class, and I was like, hey, JavaScript has a prototype-based object system, except in ECMAScript like recent, where there is a class system. But yeah, the prototype system came from Self. So that's the philosophical roots of this. Also, Self did a bunch of really interesting. So Self was a research project, and they were trying to like push the envelope on a bunch of things. And another thing that like sort of Self pioneered was this idea of like just-in-time compilation style techniques. And so a lot of the like initial ideas that then made their way into languages like Java first got done in Self. And in a later lecture, we'll talk about object implementation and tell you a little bit about some of the ideas that they came up with. Okay, so how are we going to do this? So everything is object. Messages are a good idea, so we're still going to do messages, but no classes, no variables. Another way of pitching this is that Self is a language for Smalltalk runtime structures. So we drew all these diagrams, right, where there were like these boxes, and they pointed to other boxes, and Self wants to be that. Self wants to let you represent these boxes, but they're not going to tell you like that you have to have a class parameter on your objects. Like that's up to you. So how are we going to do this? So we need a bunch of functionality, and some of it looks very familiar, right? So we need a way to send messages to objects, but we're not going to have a class. So we're going to need some way of actually creating new objects, and in Self, this is going to be done via clone. By the way, this is why it's called prototypes, right? The prototype is a sort of impoverished version of the object you're going to create that you can clone and use to then fill out with the actual information. And then we're going to have a bunch of slots on these objects which we'll interact with to store our instance variables. So objects consist of named slots, and so we're going to, so in Smalltalk, the slot, the fields on an object could just literally be like integers and strings and stuff like that, right? But we said no classes, no classes. So we need a way of actually representing what the behavior should be. And so we're just going to store that code directly in the slots in the objects. So there are going to be a bunch of different types of code we can put, right? We can have like data slots, which basically when you send a message to them, they just say, okay, here's what the content of that field was. We might want assignment slots, which basically say, hey, set the value of this slot to something else. We could have regular good old honest to goodness methods, which give you some code to run. And we can also have some, and so this is also important, we might have a parent, right, where we want to defer operations on some slots to some other object because we don't actually want to be copy pasting everything. Inheritance is still useful and we still want to support some form of it. So here's how it's going to work. So we are going to have parent pointers on our objects. And so when we send a message to an object, we are going to search for a slot with the name of the slot in question. So for example, in this example here, if I send X to the object on the bottom, I'll find, oh, there's this slot that's called X, and the code for that slot is basically return 3. So I'll get back 3 when I send this message. And if I don't find the slot, then I will recursively search the parent pointer looking for it. So if I say pass the message print to the object on the bottom, there's no print field here. So I'll go up the parent and then I'll look for the print field there. And then I'll eventually, when I find it, I'll evaluate the code in the slot to actually do the operation in question. And of course, self, which is the eponymous name of this language, points to the message receiver. So it's a special identifier, right? And lets you go back to the original object in question. And this is like the virtual method calls we talked about earlier. Okay. So one feature of self is that variables were not dumb. So everything is done with messages, right? So you can always override the behavior of what a slot does. So here is an example of the points class. Once again, you might be sick and tired of points, but I love points. And here I have one object where I have a good old-fashioned 4 and 17 stored in the x and y. And so, I've literally drawn in 4 as the value for that slot. But I also could have a random point, and this random point in the slot for x doesn't store an actual number. It could store, say, a code for doing random number generation. And now every time I query what the value of x is on this point, I could get a fresh random variable out in the situation. So like, if everything's a message, then it's logically the case that you can make things that otherwise look like good old instant variable access do interesting things at runtime. Sort of like get attribute if you're working in Python. And the x:, y:, these arrow things, right? They're just replacing what the value, aka the code in the slot, does in those situations. Okay, so how do we create objects in self? So to create a new object, we're going to copy an old one, aka the prototype. So we copy the object, and then we can add, modify, remove methods. We can even change the parent pointer, right? Because it's just data on the class. And I've got an example. So in JavaScript, right, when I create an object using the special syntax new f, what this implicitly does is that it creates the object in question and then sets the proto field on that object to point to the prototype field on the function itself. And you can do this explicitly using object.create and then pass in some prototype, and you can just manually set the prototype to point to whatever you want. This is kind of weird, and like, you probably don't use it that often, but it is possible to do. Unlike self in JavaScript, not everything is a message. So for example, you can call functions and, it's a mix of imperative and object-oriented code. So the this keyword is only defined if you actually, call the method on an object. So so how did self work out, right? So self is good in the sense that it's simpler. You don't need meta classes. You don't need the crazy stuff that happened with Smalltalk. One downside of self is it's less structured, right? We said you can do whatever you want, hooking up your prototypes, parents, and we're not really going to stop you. And that means that you have to be a disciplined programmer to write your code. For example, if you only ever use class style patterns, then self isn't going to help you enforce that that's the case. You have to do it yourself. And, this is one of the reasons why ECMAScript 6 added classes. It's kind of like, well, doing this programming manually with prototypes, it's kind of a drag. And like, it would be nicer if, you could use this other construct and it always works the same way. I finished on time. Okay, so that's it for object-oriented programming, and I will talk to you more about objects next week. Talk to you next time.